James Webb Space Telescope has unveiled a groundbreaking discovery about Simp J, Simp 0136, a massive, free-floating super-Jupiter drifting through space. Unlike planets that orbit stars, Simp 0136 exists in isolation, making it an ideal subject for studying gas giant atmospheres in their purest form. For years, astronomers suspected its atmosphere was unique, but lacked the tools to analyze it in detail. Now, Webb's advanced infrared instruments have revealed a dynamic, ever-changing atmosphere, featuring swirling iron clouds, silicate particles, and extreme temperature shifts. In this video, we'll explore how Webb captured this data, the wild weather of Simp 0136, and how this discovery is transforming our understanding of exoplanets and planetary evolution. Simp 0136, located about 20 light-years away in the constellation Pisces, is classified as a planetary mass object, meaning it has the size and characteristics of a planet, but does not orbit a star. This makes it significantly different from gas giants like Jupiter and Saturn, which are heavily influenced by their parent stars. Without a star's radiation interfering with observations, this planet provides an unprecedented laboratory for understanding how gas giant atmospheres behave independently. Before Webb, observations of Simp 0136 were limited. NASA's Hubble and Spitzer space telescopes had detected some brightness variations, suggesting a complex atmosphere, but the data lacked detail. Scientists suspected patchy clouds were rotating in and out of view, but they had no way of confirming this theory until Webb entered the scene. With its powerful near-infrared spectrograph, NARSPEC, and mid-infrared instrument, MIRI, Webb was able to break down the light coming from Simp 0136 into thousands of data points, mapping its atmospheric composition in unprecedented detail. Over a 3-hour period on July 23, 2023, Webb's NIRSPEC instrument collected 5,726 spectra, each taken every 1.8 seconds. This level of precision allowed scientists to track how different wavelengths of infrared light changed as Simp 0136 rotated. The rotation period of this planetary mass object is only 2.4 hours, meaning scientists could observe its entire atmosphere multiple times in a short span. Immediately after NIRSPEC's observation, MIRI followed up with additional data at longer infrared wavelengths, revealing deeper layers of the object's atmosphere. By analyzing this enormous dataset, scientists could construct a time-lapse view of this planet's atmosphere, tracking changes in cloud cover, temperature fluctuations, and chemical composition. The results were far more complex than expected. Not only did Simp 0136 have clouds, but its entire weather system was chaotic, featuring swirling metallic elements, temperature variations, and shifting molecular patterns. This was no ordinary gas giant. It was a stormy, turbulent world filled with extreme atmospheric conditions. The biggest revelation from Webb's data was the multi-layered nature of Simp 0136's atmosphere. Scientists found that different types of clouds formed at different altitudes, creating a constantly shifting and unpredictable atmospheric structure. The lower atmosphere was rich in iron particles, forming dense clouds of metallic vapor. These clouds behave in ways we cannot even observe in our own solar system. They likely rain molten iron when they condense. Above this layer, higher altitude clouds were composed of tiny silicate particles, similar to fine grains of sand or glass. These clouds were not uniform. Instead, they were patchy, meaning that as the planet rotated, different parts of its atmosphere came into view, creating rapid fluctuations in brightness. Scientists realized that clouds alone could not explain all the observed variations. Something else was at play. They found that this planet also exhibited significant temperature fluctuations in its upper atmosphere. These hot and cold spots moved independently of the cloud patterns, suggesting that deep atmospheric currents, or even auroras, could be shaping its weather. The presence of auroras is an especially exciting possibility. This planet has an extremely strong magnetic field, similar to Jupiter's, which could be driving powerful electromagnetic interactions in its upper atmosphere. If auroras are present, they could be contributing to localized heating, creating bright infrared emissions in specific areas. This would make Simp 0136 the first planetary mass object outside our solar system, where auroras have been detected in the infrared spectrum. Another unexpected discovery was the variation in carbon chemistry. Normally, atmospheric carbon molecules like carbon monoxide and carbon dioxide remain relatively stable, but in Simp 0136, their abundances seem to change over time. This suggests that active chemical reactions are taking place, possibly influenced by rapid temperature shifts or deep convective currents transporting materials from the lower atmosphere to the upper layers. The overall picture that emerges is one of a constantly evolving, dynamic world. This planet's atmosphere is not static. It is shifting and changing, responding to complex internal and external forces. This challenges previous assumptions that gas giant atmospheres remain relatively uniform and highlights the need for more long-term studies of exoplanetary weather patterns. Many exoplanets are studied using transit spectroscopy, where scientists analyze the light filtering through a planet's atmosphere as it passes in front of its star. However, Simp 0136 proves that a single snapshot of an exoplanet's atmosphere may not represent the entire planet. If planetary atmospheres are constantly shifting, our current models may need to be updated to account for these dynamic and evolving weather systems. Recent Webb discoveries suggest that chaotic atmospheres may be common among planetary mass objects. One of the most remarkable examples is VHS 1256b, another free-floating planetary mass object with an intensely active atmosphere. Like Simp 0136, it has swirling silicate clouds, carbon monoxide, methane, and water vapor constantly shifting due to deep atmospheric currents. Webb revealed that hot silicate grains rise into the upper atmosphere before cooling and falling back down, essentially creating a sandstorm in space. The study of VHS 1256b confirms that rogue planets can have wild, ever-changing weather systems, challenging the traditional view of gas giant atmospheres as relatively stable. While Simp 0136 does not orbit a star, Webb has also studied exoplanets that do, such as WASP 39b, a hot Jupiter where the telescope made the most detailed atmospheric analysis of an exoplanet to date. Scientists detected carbon dioxide, sulfur dioxide, water, and other molecules, revealing a surprisingly dynamic atmospheric chemistry. The ability to detect shifting carbon chemistry in WASP 39b reinforces the idea that exoplanet atmospheres may be far more complex and unstable than previously believed. These findings suggest that atmospheric reactions could happen on much shorter timescales than expected, meaning the chemical composition of an exoplanet could change dramatically over time. Webb has also provided new insights into brown dwarfs, objects that fall between planets and stars in terms of mass. Some brown dwarfs exhibit patchy clouds, auroras, and extreme winds, similar to the atmospheric behavior seen on Simp 0136. For example, Y085 5-0714 has been found to have water ice clouds, proving that complex weather isn't exclusive to planets. Meanwhile, studies of Lumen 16b, a nearby brown dwarf, suggest that it has atmospheric banding similar to Jupiter, indicating large-scale circulation patterns. These findings suggest that chaotic, fast-changing atmospheres might be a defining trait of planetary mass objects and brown dwarfs. blurring the distinction between gas giants and failed stars. One of the most significant aspects of Webb's study of Simp 0136 is its connection to upcoming space missions, particularly NASA's Nancy Grace Roman Space Telescope, set to launch in 2027. This telescope will specialize in directly imaging exoplanets, using techniques similar to those applied to Simp 0136. By refining these observational methods now, Webb is preparing scientists for the next generation of exoplanet atmosphere analysis, which could help us detect potentially habitable worlds. Webb's discovery of Simp 0136, along with similar findings like VHS 1256b and WASP 39b, is revolutionizing our understanding of planetary atmospheres. These objects are not static worlds, but turbulent, ever-changing environments where silicate storms, shifting temperatures, and even auroras may be the norm. With future missions set to expand our ability to directly image exoplanets, we may be on the verge of uncovering the true complexity of alien worlds, and perhaps even finding one capable of supporting life. Thank you for watching. Stay curious, keep exploring, and as always, keep looking up. As telescopes like Webb continue to explore the cosmos, we are getting closer than ever to answering some of the biggest questions in planetary science. What do you think? Could these same methods help us discover a truly habitable exoplanet? Let us know your thoughts.